It was like find the eigenvalues. We was talking about degeneracy, right? And let me know by turning on your speaker if the board is not visible or if there is problem any time during the lecture. So, as I said, I am going to repeat briefly the last example that we discussed in the previous lecture. So that is kind of a very quick repetition. Right? The operator was like this: 1 0 1 0 2 0 1 0 1. Right? And we were to find the eigenvalues and eigenvectors, and we saw that there was a degeneracy in the eigenvalues. There were two eigenvalues, they were identical, right? So that is called the degeneracy. So if you have to solve example 1.8, whenever you have to solve an eigenvalue problem, you write the circular equation, right? The eigenvalue problem is it is like, you know, omega is like our eigenvalue. Suppose omega is our eigenvalue. And suppose omega vector is our eigenvector. Then we will write the eigenvalue equation of this, like, you know, just working on this, giving some eigenvalue omega to you and giving the same eigenvector, right? Or we can write this as omega minus omega I, right? And omega is equal to 0. We did that before. And for solving, we want to solve for omega, right? We have to find the circular equation or the characteristic equation, the circular equation, right? In your matrices. And it is like the determinant of this. So this would be 1 minus omega, right? 1 minus omega, 2 minus omega from this subtracted from the diagonal, right? So it would be like determinant of this 1 minus omega 0 1 0 2 minus omega 0 then 1 0 1 minus omega. That is equal to 0, right? If we solve this determinant, right, we will get a polynomial of GP3, right? And we got by solving this, you have to write this and cross this, and then multiply by this minus this, with respect to this, then with respect to this. Then, if you remember, we got omega is equal to 0, and it was 2 and 2. Right? Okay, so these were the two values, right? Now, how to find the eigenvectors? So we found the eigenvalues. Now, how to find eigenvectors? Omega is equal to 0 and the 2. So here there is a double degeneracy, right? Here will be one value 2, which has two states. Right? So how to find them? We put, for example, we want to find there is at least one eigenvector for each eigenvalue. This was kind of we discussed it before. So let us find what is the eigenvalue, the eigenvector corresponding omega is equal to 0, right? And so we suppose denote it by this. That is the eigenvector corresponding to the eigenvalue, right? So we put it back in the matrix equation. Omega is equal to 0. We pull it back. In this equation, the matrix equation, omega is equal to 0, and then we multiply it with V1, V2, V3. I'm not repeating that. We have done it many times, right? And we get what vector we got. It was like the vector was 0 is equal to 1 over 2 square root 0 and minus 1 over 2 square root. Right? We can take 1 over 2 is constant. So 1 over 2 square root, and that will be 1, 0, minus 1. This is the eigenvector corresponding to omega is equal to 0. Right? Now, what is the value, the eigenvector for omega is equal to 2. So is there is a double degeneracy? If there is a double degeneracy, so there will be two states. So let those two states, let us represent them by 2, and suppose they represented by 2 prime. Suppose one is 2 and other is 2 prime. So to get, suppose 2, we put this omega is equal to 2 back in the matrix equation, right? In the matrix equation 1, sigma j, right? Omega ij minus omega delta ij, right? And 2 vj is equal to 0, right? Was kind of like this matrix 1, 0, 1, right? 0, 2, 0, 1, 0, 1. This matrix or this, right? And minus omega I. So omega I will be like omega 0, 0, 0, and sorry, omega is 2. So put it 2, 2, 0, 0, 0, 2. Right? This is for this. And here, Vj. So V1, V2, V3. That is equal to 0, 0, 0. Put on the matrix equation, right? So we can write this as I will be like 1 minus 2. So that will be minus 1, minus 1, 0, 0, and sorry, 1, and 0, 0, 0, 0, because 2 minus 2 will be 0. So 0, 0, 0, then 1, 0, 1, 0, and then 1 minus 2, so that will be minus 1. Right? And it will be V1, V2, V3, is equal to 0, 0, 0. Right? Now this gives us three equations. Generally it should, right? But let us see what is the situation here. So it is like minus V1 plus V3 is equal to 0. This will give us nothing. This is meaningless. This one will be V1 minus V3 is equal to 0. Right? So this is the same thing. So we are not getting generally if we have three unknowns, so we need three equations, three linearly independent equations to know the three unknowns. Here we have only one equation, three unknowns and one equation. So we have freedom, to select the two. Okay, so this equation gives us V1 is equal to, we have one equation. We have one equation and three unknowns. So we are free to select two, whatever we like. Right? With this condition. Generally, here it would be like something, right? I can select something like this. V1 is equal to V3. So instead of V3, I should also write V1. For V2, I'm completely free to write whatever I like. So let me write as 1. Right? These are two the same thing. Right? Two the same thing. Since this can be multiplied with any scalar quantity, and that will represent the same vector if it is multiplied by a scalar. So I can write this as 1 as well. Is equal to some 8 times 1, 1, 1. The condition, we got this by choice. We are free to put x to anything we like. Not x2 is in your book. We do. We are free to put V2 at any number. But this condition should be there. The first component, the first element, and the third element must be the same. Right? So we can put V1 and V2 as we are again free to write V1 whatever we like. So we write it as 1. Now, if we want to normalize this, we can find the value of A, right? And the value of A will be like, you normalize it. When you normalize it, right? It will be A star into 1, 1, 1, and then A, and 1, 1, 1, and that will be equal to 1, right? So that will be A square, and this will be 1 plus 1 plus 1, that will be equal to 3. So equal to 1. So A will be equal to 1 over 3 square root. Right? So now, my first vector 2 will can be written is 2 is equal to 1 over 3 square root, right? And 1, 1, 1. That is my first eigenvector of this operator for the eigenvalue omega is equal to 2, right? Now, for the third vector, I should say, what will be this now? 2 prime. Right? What will be that? The vector this must be perpendicular to this one. This one. Right? Because this form a basis. So this vector must be perpendicular to this. What we have in hand, only this thing. And this is completely free. So we can find, if we want to know what is, we are interested in finding a basis. And a basis would mean all the vectors must be perpendicular to each other. They must be orthogonal, like I, J, K. This form a basis, I, J, K form a basis, three-dimensional basis. And they all are orthonormal. The magnitude is 1, and I is perpendicular to J, J is perpendicular to K, K is perpendicular to I. So if we are interested to find a second eigenvector of the same eigenvalue, which will form a basis, then it must be perpendicular to it. To this one. Let us find what is that. So it should be of the form, right? It should be something like this, right? And here we should be of the form this. You can write A here because we don't know. Should be of the form this. We have only a freedom of completely unknown quantity is this, the second one. V2 completely free to select. There is no condition on it. There is no last connection. There we are. Little dark. Okay, so we are free from the condition. We have only one condition upon us, and it is this. For V2, we are completely free to select whatever we like. Let us we put it as V2. So to find a second vector which is perpendicular to this one, these two, the scalar product between these two must be equal to 0 because they are perpendicular. And the scalar product will be something like this. 2 and 2 prime should be equal to 0. Right? Okay. So I can write the situation here. 1, 2, 3. And when I just change it to bra, I have to make it like take the rows into column. Right? So that will be 1, 1, 1. And for 2 prime, I write it A and 1, V2, and 1. And that should be equal to 0. This can be written in A, 4, this square root, right? and 2. There will be 1, 1 plus V2 plus 1 again is equal to 0. You can multiply this both the sides by 3 square root divided by a. Therefore, this goes out, and you get 1 or V2 plus 2 equal to 0. Right? So you get here V2 is equal to minus. So now the second vector with the same eigenvalue in this case two prime is equal to, I put the value of V2 here, a 1 minus 2 and 1. This is orthogonal to this. Now let us normalize it to find a. So we will say there will be a squared 1 minus 2 1 and 1 minus 2 1, that will be equal to 1 to normalize. So a squared and to that will be 1 1 4, so that is 6, right? So a will be equal to 1 over 6 cubed, right? So to the prime, I will say the second vector, right? That will be equal to 1 over 6 square root and 1 minus 2 and 1. So that is the kind of the third vector. What is this one? Right? These two are, they form a set of two-dimensional bases in which the vectors are, one is this vector. This is, for example, I, and this is J. I and J. Corresponding to the eigenvalue, omega is equal to 2. Corresponding to, for the degeneracy, we have two vectors. We found it like that. This is called degeneracy. There are two different vectors. There are two different vectors. And they correspond to a single value. So we can say that this lies in a subspace. You know, there is an omega operator. Omega operator has 3 eigenvalues. So it must have a basis which contains 3 vectors, in which 2 vectors onward form a basis which correspond to the eigenvalue omega is equal to 2. This is called degeneracy, right? So in degeneracy, we are free. We have an infinite number of bases. It will not change the result. We have infinite number of bases. We are free to select anyone from those infinite, like this. You know, we selected it like we say here V2 was completely, the value V2 was completely free. We selected it as 1. So for day, we got 2 vectors which were perpendicular mutually, right? It was like 2 and 2, 2 prime. This is the basis. Now, to give this another number will be like rotation of the frame. So you can have another basis like this. You can have another basis like this. You can have another basis like this. All are perpendicular. This is perpendicular to this, or I will say this is perpendicular to this. This is perpendicular to this. This is perpendicular to. So I'm in the middle. I have infinite number of choices to select a basis, and this is what degeneracy gives us. Degeneracy gives us the freedom to select our basis from an infinite set of bases. Right? So this was the problem that we were solving in the previous lecture, and was messed up. It was not clear. Okay. Now we want to go a little further, right? Serial number 11. This theorem states that the eigenvalues of a unitary operator are complex number of modulus 1. You know, if you remember, we said a unitary operator is kind of a rotation operator, but in n dimensions. Unitary operator is a rotation operator. Right? So it says the eigenvalue of a unitary operator are complex and they are of modulus 1. So look, rotation, unitary means rotation, and rotation means oscillations. And oscillation means complex values. Oscillation means complex. It makes sense that the rotation operator has got complex values, eigenvalues, right? And they correspond to oscillations too, an oscillating system. So, suppose we have a unitary operator U. We have a unitary operator U. And suppose U is its eigenvector. U is its eigenvector. And suppose this U, small u, I should write it like this. Small u is its eigenvector. Suppose we have two eigenvalue equations. Suppose we have two eigenvalues of this operator. Suppose we have two eigenvalues of this operator. So it would be like this. Acting on this, one is equal to u1 and to u2. Right? Question number 1. Since we said, suppose this has two eigenvalues, let the other eigenvalue is u2. So u operator, unitary operator, and let the corresponding vector is u2. This is equal to u2, u2. We have the same operator. Suppose it has two eigenvalues, u1 and u2. We can write the eigenvalue equation for the first eigenvalue. We can write eigenvalue for the second eigenvalue. And these are the different eigenvectors corresponding to the different eigenvalues. Right? Now, suppose we take a joint of adjoint of 2, right? So we take adjoint of 2, it would be like U dagger, right? And this will become what? It will become broad, right? And this will become complex conjugate of that U2 eigenvalue. This will also become broad. So you can write this is the scalar quantity. What do we join now? Okay, so I am taking the adjoint of this. So the adjoint of this will make U dagger. This is the scale quantity, so we should take the complete conjugate of this. And therefore, that will also be changed to so I think the scale product are you people hearing me? Someone can turn on the mic. Sadiq?
Yes, sir. सुन रहे. Yes, sir.
All
We
right?
can hear you now.
Huh?
Sir, there
Sir,
is breakage in
अभी आपको
between.
Something is missing?
Yes, sir.
Okay, look, we can everything. So uh, let us follow whatever is. The last lecture was also interrupted a lot, many times. So hope we will get something out of it, right? Board photo, Razi, was the board photo kari ka na?
जी
Yes,
Okay,
sir.
सर.
Board
so
जी
Khali.
सर.
board is visible. Okay, so suppose generalize it. Suppose I is equal to 1 and j is equal to 2. So generalize. So we can write them like u j and u data u and u I and is equal to u j and then scalar quantity u I, right? And uj and ui. Right? Now we know that u Dagger and u are identity matrix. So we can write this as uj and ui, right, is equal to uj star ui uj and ui. I bring this to the side and write it like this: 1 minus uj star ui and uj ui, and this equal to 0. Right? We said that the eigenvalues of a unitary operator are complex. These are the eigenvalues. They are complex. Right? So, suppose I is equal to j. Suppose they are the same thing. When I is equal to j, then this cannot be equal to 0. Then look, ui into ui is not equal to 0. When that is not equal to 0, then the only choice is that this is right. So 1 minus ui star, remember I replacing j by I, and these are the small u. These are the eigenvalues, not to map the operators. This is equal to, this means that 1 is equal to ui star into ui. So look, 1 is equal to ui star and ui. It means that there are complex numbers, because the product of these complex numbers is equal to. And also, if you take the modulus, so this will be equal to 1 square and 1 square root of 1. Ui will be equal to square root of 1, and square root of 1 is 1. So it is a complex number, and it is the modulus is equal to root. The eigenvalues of unitary operator is a complex number because u star u gives us real. So it's a complex number. Second, if you take the modulus of this, so ui will be equal to, because 1 square root equal to, right? So that is how the theorem is proved. Theorem number 12. Right? Theorem number 12 says that the eigenvectors of a unitary operator, we have a rotation operator. The eigenvectors of the unitary operator are orthogonal. They are perpendicular. If we have a unitary operator, their eigenvectors are orthogonal. Suppose we said 1 is one eigenvector, and this is another eigenvector. So this theorem says that u1, u2 should be equal to 0. Here, scalar should be equal to 0, which means that they are orthogonal, right? So let us prove it, right? Our last equation was 1 minus ui star, sorry, uj star ui, right? And uj ui, this was equal to 0. That was the last equation. Question 3 or some other, I don't know. Question 3? No, correct. Whatever. Equation unknown. Right? So we take different eigenvectors. So for this, I is not equal to j. I is not equal to, right? When I is not equal to j, then ui is not equal to uj. They are different. When they are different, then the eigenvalue ui is not equal to uj. Right? They are not equal to uj. And when they are not equal, from theorem number 11, right? Theorem number 11 says when they are equal, it is equal to 1. But if they are not equal, so it means ui and uj star is not equal to 1 because I is different from j. So when this is not equal to 1, it means this is not an option. This is not equal to 0. When this is not equal to 0, the only option left with us is this is equal to 0. So uj and ui is equal to 0. Or we can say u2 and u1 equal to 0. Or if we say u1 is perpendicular to 2, right? Now there is an interesting situation. If you want to solve problem, right? Like you in your electromagnetic theory, for example, you want to solve problem of a sphere of some charge density rho, and you want to find the electric field inside or outside, So you will have to use Laplace's equation, suppose. Laplace's equation is a differential equation. Then you will have to use some coordinates, x or y, or you will have to use r and theta. If you use x and y, solving that problem will become very difficult. So a very intelligent person, if he wants to solve the problem, he would use an appropriate set of coordinates. He would use r and theta. Because that is a very easy, in using xy, you can solve the problem, but it will be like very difficult, very consuming, time consuming, and will demand a lot of labor. If you use r theta, the problem will be easy. If you use polar coordinates. Similarly, if there is a plane, right, and you have a charge density over a plane, or something of a rectangular shape, it is better to use the rectangular set of coordinates x, y, z. So it is always good to use a set of coordinates for solving a problem, which makes your problem easier, which makes your job easier. Similar is the situation in quantum mechanics. We have different bases, different kind of set of coordinates. I, j, k, x, y, z, r, theta, phi, whatever. Right? So we have to use a set of coordinates, a basis, which makes our problem easier. This situation is called, in mathematics and quantum mechanics, diagonalization of the operator. Diagonalization of the operator. This makes the operator in the easiest basis. By diagonalizing an operator, by diagonalizing a matrix, you represent the operator in its easiest basis, in its eigenvectors. So this situation is called diagonalization. The mathematics becomes very simple as well, because there are only values in the diagonal places. Matrices have this situation. To diagonalize an operator, to diagonalize a matrix, is called similarity transformation. Right? Similarity. Similarity transform. Similarity transformation or diagonalization of Hermitian operators. We are interested in Hermitian operators because Hermitian operators they correspond to our observable. ये मोमेंटम भी आपको देता है, ये आपको एनर्जी देता है. Hermitian operator ना हो तो फिर it is not of our interest. Of Hermitian operator. Right? So if we have, if we have some basis, orthonormal basis, omega, 1, 2, 3, some I, some n. We have an n-dimensional basis, and these are orthonormalized bases. This is like x, y, z. Orthonormalized, right? And we have an operator. We can represent, or this operator, or this Hermitian matrix, Hermitian operator can be represented in this basis. And then these bases, according to that, this will form the elements of the matrix. Right? This matrix, we can form this. We can write this matrix in the form of its diagonal. Suppose this is a matrix and this is some basis. And so this is a matrix, this is an operator. It will have omega i's eigenvalues. Operator, eigenvalues. And eigenvalue, so that it will have eigenvectors. Omega 1, omega 2, omega 3, and so on. It will have eigenvectors. So it is better to represent this in the form of in the basis of its eigenvectors. Right? एक spherical polar coordinate system के लिए अगर हम very rough example ले लें, इसके लिए eigenvector इसके r theta phi होंगे. right? So we can represent, if it is given in this, we can change it to this. If this is given in this, we can change this. This is called diagonalization of. Then this will be given in the form of a diagonal, right? And what is the what is the process? It is called rotation. In quantum mechanics, we rotate the basis. We rotate our system a little bit. You know, in classical mechanics, you are after solving a problem. You know, there are different situations. You can choose your origin anywhere. Sometimes you can choose your origin anywhere. It should not choosing the origin should not introduce any change in the result. So you can change your origin, you can change your coordinates, you can rotate. So by rotating the coordinate system, we can make a matrix appear in the form of its diagonal vectors. So the process is like this. You take a rotation operator to the matrix omega that we have, and then sandwich it between you, right? This process, sandwiching it between U taker and U, the unitary operation, makes this vector diagonal. And diagonal is all the values are 0 except the values at the diagonal. So that's the product becomes easier, mathematics becomes easier. And it is in the form of its eigen. Now this, this will give, this is a matrix, this is a matrix, this is a matrix. This will give you another matrix. Right? This is the diagonal matrix. This thing, D, is the same as omega. D is the same as omega. But omega is in this basis, some basis, and D is in the eigenvector basis. So these are the same. Omega and D are kind of the same. The only difference is you are using different bases. इसमें आप XYZ इस्तेमाल करते हैं, इसमें आप theta phi. T is the same है, derivative the same है, right? So this is called similarity transformation. When you change a matrix from any basis to be represented in the form of its eigen values, and it is in diagonal form. This situation is called diagonalization of the matrix or similarity transformation, right? And this makes our problem easier. This makes our life easier. Right? Some homework problems. Let's do. Hopefully, we will be able to take our next classes in kind of face to face, not problem are not issues of internet, and we will speed up a little bit. So see you next time. And there's a homework, so you try them, right? These are like your practice for what we do, the eigenvalue problems. These are for the practice for the eigenvalue problem. So I'm stopping the recording. If you have any question, you can ask me.